So we're doing lesson 7 here. And there are four objectives that we have in lesson 7. They're roughly this. Oxidation of alcohols, ether cleavage, how we're going to cleave ethers, epoxides, and cis-trans diols. Okay. So first of all, with oxidation of alcohols, let's define what we mean by oxidation. And this is not necessarily the same language that we used in organic or in Gen Chem, but oxidation is generally going to be more carbon-oxygen bonds or less carbon-hydrogen bonds. Okay? And reduction is just the opposite. Less carbon-oxygen bonds and more carbon-hydrogen bonds. Okay? So that's generally what we mean by oxidation. So let me give you an example of that. If you've got, say, 1 propanol, you've got 1 carbon-oxygen bond here. But if you change that to 2 carbon-oxygen bonds, that is propanal, right? Propanal. Okay? 1 propanol. Alright, so indeed we start out with 1 carbon-oxygen bond, we end up with 2, and by this definition that's an oxidation. I think it's really good to think in these terms here because this needs to be second nature to us. So you can just very easily see that. As a general rule of thumb, the reagents that are going to give us things like that have lots of oxygens in them. Okay, so for example, this first reaction that we have in Bruce is on page 499. It's section 11.5, lesson 7. It's 1 propanol, and it's chromic acid. So can you see a bunch of oxygens there, right there? Okay, so look out for that, a bunch of oxygens. Another reagent that we have on page 499 also is PCC, so it's difficult to see all the oxygens in that one. It does have it. It's pyridinium chlorochrome 8. Anything that ends in ATE's got a bunch of oxygens in it probably. So anyway, this is going to be an oxidizer, which an oxidizer in this case is chromic acid, H2CrO4. Sulfuric acid is another oxidizer. Sodium permanganate, MnO4, is another, or potassium permanganate is more common, MnO4. KMnO4, sorry, it's not 2. Permanganate only has -1 on it. So these are oxidizers, and you want to get used to that. So section 11.5 is oxidation of alcohols. I think you ought to do something like this. I'm not going to give you this sheet myself. You need to make this up. Section 11.5 has got these 4 new reactions in it, and these are just oxidation reactions. There's one last thing I want to say about that before we move on, and that is that a strong oxidizer, which I'm going to put as an oxidizer with an exclamation, 2 exclamation points, make it obvious, okay? A strong oxidizer is going to take something like, 1 propanol, and it's going to take it to propanal, but you can't stop there because it's a strong oxidizer. So what it's going to take it to, it's going to oxidize it even further to propanoic acid. Have a look at that, okay? But a weak oxidizer, which I'm going to sort of making up notation here, okay? I'm putting a question mark there to sort of, a weak oxidizer can stop there, all right, and it doesn't go any further. Can you see that this is oxidized further than that? All right, and this is not. By the way, what's the ultimate oxidation? That's not. If we have, if the definition of oxidation is more carbon-oxygen bonds, if that's the definition of oxidation, I have how many carbon-oxygen bonds here in propanol? 1 propanol, 1. There are 2. Here's 3. So the ultimate oxidation is what? That's a good question for you to think about. What is the ultimate oxidation? It's a little bit tricky. Maybe it's not a fair question. But it is something to think about, and there is an answer for that. All right, so that's oxidation. That's the first objective for this lesson, oxidation of alcohols. The second objective is ether cleavage. And I want to ask you a question. Ether cleavage here looks a lot like what? That's a question for you to answer. So let's talk about what we mean by ether cleavage. Ether cleavage looks like, here's just the simplest ether. We always try to think about these things in the simplest terms first. And the mechanism looks like this. HX, boom, boom. Right? There's a plus on there because oxygen's got 3 bonds and 1 lone pair of electrons. Alright, now that said, it makes a partial plus on that carbon and a partial plus on that carbon. They were already a partial plus on there, right, because electronegative element. But the fact that we've got a proton on there makes it even more. And that's going to take this guy here and that guy there. Okay? And that gives us methanol and an alkyl halide, a methyl halide, really specifically. Okay, so that is one ether cleavage. That looks a lot like what we've seen a reaction recently. So my number one question is, looks like. You think about that. Be ready to answer that on a quiz. I don't know that it will show up in the quiz. I'd like to put it on there. If I remember, I will put that on the quiz. What does this look like? Something you've seen before. I don't mean does it look like a Mack truck or a freight train or an airplane. I mean, what reaction have you seen before that looks like this? Okay? And there is an answer, and it was very recent. All right, and the next question I want to ask you is, what's this mechanism? What's the most general name for this mechanism? I mean, we could give it very specific. We might call this mechanism ether cleavage by hydrohalic acid. But more generally, what is the name of that mechanism? Something we've seen before. I'll give you a hint. We don't have a video up of it, but we've talked about it in lab and also in class. Okay, so that's ether cleavage. I'm afraid that's the answer to one of the questions I asked you. Okay, the next objective here for lesson 7 is epoxides. And I want to ask you also, this looks a lot like what? So epoxides are here, right? And these come from something else. You should be asking yourself, what do they come from? That's something from Organic 1. It's on your list of reactions that you're supposed to know. Now, epoxides, you would, as you might imagine, have a partial positive here and a partial positive here for the same reason that the ethers do, right? These have partial positives because they're on an electronegative element. This one's even more reactive, though. Why? Why is this more reactive? Why is this more reactive than an ether? Okay. Give you a hint. We are always answering questions like this based upon 2 criteria, structure and polarity, right? So think about those. Why is that more reactive? All right, and the next thing, so what we have, right? If we got that, we've got that right there. Then what we have with the reactions that we have for ether cleavage are, we could also do this with a hydrohalic acid. Oops, that's not a lone pair anymore. It's a bond. Partial positive on there. This makes this even more vulnerable. This one over here is the same, by the way, as I've got it. That makes that even more vulnerable to the... Right? And what is this called? What is the name of this? I really, when I ask those questions, I really do want you to think about that. Maybe pause the video. I'm about to say what it is. What is this called? It is a halohydrin. What? It's not a question mark, sorry. Halohydrin. Have you seen that before? Yes, yes we have. I don't remember what section that's in. I think it's in chapter 6. Okay? Making halohydrins. This is an alternate way to make halohydrins, and I'm going to ask you what... So I've got a question here. with epoxides. What can we do now? How is this different than what we did before? So before we took this, and we treated it with bromine and water, and we got a halohydrate. Okay, and here we're doing this, and we're treating with MCPBA as an example of a, maybe that might be something you want to look up, a per acid. And the second thing we treat it with is HBr, and we get boom and boom. What's the difference between those two reactions? An important difference. Give you a hint. Look at the mechanism. Okay? This is a synthesis thing. You need to look that up and figure out why those two are different. Okay, and the last thing I want to talk about for lesson 7 is cis-trans diols. So this sort of is a kind of a funny thing to have here because it's not necessarily having to do with epoxides or alcohols. One of them doesn't, but it's one way of making those. So, okay, if we take that and we treat it with that, this is going to come there and go there, just like you might expect, right? And it's going to give you an OH, and then if you treat that with water, then you get, okay? Now if you look at the mechanism there, you can see this is coming in from the back side of that. So this is going to give us a trans diol. Now it doesn't matter here, if we're just dealing with ethanol, it doesn't matter because there's free rotation about that bond. But it does matter if we've got substituents on there. I mean, if these are just hydrogens, it doesn't matter. But if we've got two substituents on there, A and B, and A and B, hey guys, A and B, then we're going to get something different than if you had if you switch these two, right? This is now all of a sudden, well, this is probably going to be racemic, but or a meso compound. But say A, B, B, and C, then it's going to matter if it's trans or cis. Of course, also if it comes in as if you've got that also. That's another time when you can definitely tell if it's trans or cis. Then the other reaction we have is with an alkene and osmium tetroxide. Okay, and that gives us a cis diol. Okay, so that's lesson 7, and those are our 4 objectives. Our 4 objectives were oxidation of alcohols, ether cleavage, epoxides, and then cis-trans diols.